Welcome to the Deep Dive, where we cut through the noise to deliver truly insightful knowledge. Today, we're plunging into the fascinating core of machine learning. We're not just defining terms here. We're aiming to give you a shortcut, really, to truly understand how data transforms into predictions and, the surprising challenges you'll hit along the way, and maybe why some models are like these meticulously engineered race cars, while others have a real sweet tooth for tricky data.
Yeah, that's a good way to put it.
So our mission for this deep dive, it's really to equip you with that foundational understanding, the stuff that makes the whole landscape of machine learning kind of click.
Exactly. Think of this journey as building a mental framework, maybe one aha moment at a time. We'll explore how all these machine learning concepts connect.
Okay.
Focusing on why each piece is crucial, for building robust and effective AI solutions. We're going beyond just the what and digging into the why it matters.
Okay, let's unpack this then. At its heart, machine learning. It's about systems learning from data, right? Without needing explicit step-by-step programming.
Precisely. It's like teaching a computer to adapt and improve just by observing patterns, rather than spelling out every single rule for it.
And within this huge field, our spotlight today is firmly on a key approach called supervised learning.
Supervised learning, yeah. That's where a lot of the magic really begins. Imagine you have a teacher guiding a student.
Okay.
The model learns by seeing inputs alongside their corresponding correct outputs. That's your labeled data.
Got it. Labels.
So, for example, if you want to predict whether a customer will purchase a product, you'd train your model on past customers where you already know if they bought something or not. That's the label.
Okay.
Or if you're forecasting wind speed, you'd feed the model historical data where you know the conditions, dew point, temperature, and, crucially, the actual wind speed that occurred.
So with supervised learning, we're largely tackling two main types of problems, is that right?
That's right. Broadly speaking, yes.
On one hand, you have classification. That's where the model sorts things into distinct categories or labels, like a spam filter, deciding if an email is spam or not spam. No middle ground.
Exactly. Discrete categories. And the other side of that coin is regression.
Right.
Here, instead of a label, the model predicts a continuous numerical value. Things like predicting house prices based on features like square footage, number of bedrooms.
Okay, like a specific dollar amount.
Or estimating a student's final exam score based on their study habits. Those are classic regression problems. The output can be, well, pretty much any number within a range.
Makes sense.
Now, whether it's classification or regression, pretty much every machine learning initiative follows a similar path, a kind of unified project lifecycle.
Okay, a standard process.
Yeah. It starts with clearly defining the problem, then comes data acquisition, and critically, feature engineering.
Feature engineering, that sounds important.
Oh, it's vital. This is where you transform that raw data into features your model can actually learn from. It's like sculpting the raw marble before you even start painting.
I like that analogy.
Only after that crucial step do you move into exploratory data analysis, or EDA, then modeling, evaluation, and finally, deployment. That feature engineering step really lays the groundwork for everything you uncover in EDA.
Okay, speaking of EDA, exploratory data analysis, it sounds like it's maybe more than just a checklist. It's almost an art, a mindset.
Absolutely. EDA is where you turn raw data into genuine insight. It is a systematic process, sure, but it demands an iterative mindset. You're blending statistical summaries with, powerful visualizations and a healthy dose of critical thinking.
So you're constantly asking questions of the data.
Exactly. The goal isn't just to list facts about your data, but to uncover its hidden truths, its surprising patterns, and importantly, its potential pitfalls.
So when you're actually sitting down with a data set, what are some of those key actions? Where do the aha moments really happen in EDA?
Well, you typically start with data inspection and summary statistics. This is your first handshake with the data, right? You look at its shape, how many rows, how many columns, the types of data in each column, basic metrics like mean, median.
The basics.
Yeah, the basics. But the aha moment often comes when you check the value counts for categorical features. Suddenly you spot a major class imbalance, like 99% of your data falls into one category.
Oh, okay.
That immediately tells you your model might struggle to predict that rare 1% category. That's a huge insight right there.
Right. It changes how you might approach modeling.
Definitely. Then there's outlier detection. You might think your data is clean, but a simple box plot could reveal something glaring, like a customer age listed as 200 years.
Whoops.
Or a product price that's negative. EDA finds those things that could totally throw your model off.
So it's about finding errors, but also just extreme, maybe real values.
Exactly. You need to figure out if it's an error or just unusual. And in bivariate and multivariate analysis, that's where you look at relationships between features. You run a correlation matrix and maybe find two columns are almost perfectly correlated.
Like number of rooms and square footage.
Perfect example. If you don't spot that multicollinearity, your model might get confused about which feature is actually driving the prediction.
That's fascinating, finding those hidden connections or, yeah, outright errors. So what are the biggest pitfalls then, or the best practices for ED?
A key best practice is definitely maintaining that iterative mindset. You don't just do ED once. You circle back, dig deeper as questions arise.
Keep asking why.
Yes, and always tie patterns back to domain knowledge. Is this correlation real or is it spurious? Like ice cream sales and shark attacks might correlate.
Right, but it's summer causing both.
Exactly. It's the heat, not the ice cream, causing shark attacks, a common pitfall. Focusing only on the obvious stuff. The real gold is often in the subtle anomalies. And, critically, failing to document your steps makes it impossible to reproduce.
Good point. You mentioned anomalies, but sometimes data isn't just weird, it's, well, missing entirely. Let's dig into missing values. That seems like a real headache.
It can be, yeah.
I gather the reason data is missing is often as important as the fact that it is missing. Can you break down those different types of missingness?
You're absolutely right. Understanding why data is missing is critical because it dictates how you should handle it. It affects the validity of your analysis.
Okay.
The first type is MCR. That stands for missing completely, at random. Think of it like a perfectly random sensor glitch. The chance of a value being missing is totally independent of everything else, observed or unobserved.
So pure randomness.
Pretty much.
Yeah.
If data is truly MCR, sometimes just removing the rows with missing data, list-wise deletion can be okay, though you lose information.
Makes sense. What's next?
Next is MRR, missing at random. Now this is a bit trickier. Here, the missingness does depend on other observed data, but not on the missing value itself.
Example.
Okay. Imagine in a survey, older respondents are more likely to skip a question about, say, internet usage. The missingness depends on age, which you have observed. But given their age, whether they answer or not, doesn't depend on their actual internet usage time.
I see. It's related to something you know, but not the missing thing itself.
Correct. And finally, the most challenging one, MNAR, missing not at random.
Okay, MNAR.
This is when the missingness depends directly on the unobserved value itself. The classic example is high earners being less likely to report their income on surveys.
Because it's high.
Exactly. The very fact that their income is high influences their decision not to report it. The missingness is directly related to the value you're missing. This introduces bias that's much harder to fix. It's a real puzzle.
Wow, yeah. That really highlights how complex just handling missing data can be. It's not just plugging a gap.
Oh.
So how does knowing these mechanisms, MRR, MNR, actually guide you to the right imputation strategy?
Knowing the mechanism is absolutely key because using the wrong method can seriously bias your results. It's not just about filling the blank. It's about filling it appropriately.
Right.
So for numeric data, if you're pretty sure it's FCR and maybe normally distributed, simple mean imputation might work. Just fill with the average.
Okay, simple enough.
But if the data is skewed or has outliers, the mean gets pulled around. So median imputation is often much better, more robust.
Because the median isn't affected by extremes as much.
Exactly.
Yeah.
Then you have more sophisticated methods like KNN imputation, which looks at similar data points, or even predictive imputation like MYC, where you actually train another small model just to predict the missing values based on the other features.
Wow, okay. Building a model to fix the data for your main model.
Kinda, yeah. And for categorical data, you might use mode imputation fill with the most frequent category. Simple.
Okay.
Or sometimes you create a whole new category like missing or unknown. This actually tells the model explicitly that the value is absent, which can be useful if the missingness itself carries information.
That's clever, preserving the fact it was missing.
It can be. The absolute key best practice, though, no matter the method, visualize your data before and after imputation. Always check if you've accidentally distorted the distributions.
Right, check your work. Makes sense. Okay, so we've meticulously cleaned our data, engineered features, explored it with ED, we've got all the ingredients prepped.
Yep.
Now it's time to cook.
This feels like the modeling and algorithm selection phase. It seems like a really crucial decision point, choosing the right algorithm. How do you even start?
It is crucial, and honestly, there's rarely one single right answer up front. It depends entirely on your specific problem. Is it regression or classification? What did your data look like? What are the business goals? Accuracy, interpretability, speed.
Always trade-offs. So let's start with regression algorithms for predicting those continuous numbers. The absolute foundation is linear regression.
Okay, y, mx plus b flashbacks.
Exactly. You're basically fitting the best straight line through your data points, minimizing the errors using usually the least squares method. It's simple, elegant, very interpretable, but its big assumption is linearity. If the true relationship between your variables is curved, a straight line just isn't going to capture it well.
It'll miss the pattern.
Right, and it's also pretty sensitive to outliers. One extreme point can really yank that line out of place.
Okay. What if you have more than one input feature affecting the output?
Do you step up to multiple linear regression? Same idea, but now your equation has more terms. Y plus OEX plus the Xers and so on. Predicting house price based on size, location, bedrooms, age.
Right, multiple factors.
Yeah. But here you have to watch out for multicollinearity. We touched on this. If two input features are highly correlated, like square footage and number of bedrooms,
The model gets confused.
it struggles to tell which one is really driving the price, makes the coefficients less reliable, and if the relationship isn't linear at all, you might try polynomial regression. You add squared terms, cubed terms, whatever, to let the model fit curves.
Like modeling salary growth over years, it might curve upwards then flatten.
Perfect example. Captures that nonlinear pattern.
Okay, that covers regression basics. What about classification? Assigning those labels. How do algorithms like support vector machines, SVMs, handle that?
SVMs. Very powerful, very interesting geometrically. The core idea is to find the best boundary or hyperplane that separates the different classes in your data.
Boundary line.
Exactly. But not just any boundary. SVM specifically looks for the one that creates the largest possible gap or margin between the boundary and the nearest data points of any class.
Widest possible street between the classes.
That's a great way to think of it. And those data points right on the edge of the street, those are the support vectors. They're the critical points that actually define where that boundary lies.
Okay, so it focuses on the points closest to the dividing line.
Precisely. Now, what if your data isn't separable by a straight line? Imagine red dots inside a circle of blue dots. No single line works.
Right, tangled up.
This is where the kernel trick comes in. It's a bit mind-bending, but really clever.
Uh-oh.
No, it's cool. Think of it like this. Your red-blue dots are mixed on a flat table. You can't slice between them cleanly. But what if you could somehow project them upwards, maybe into 3D space, in such a way that all the red dots end up floating above all the blue dots?
Then you could just slide a flat plane between them.
Exactly. That's what a kernel function does mathematically. It maps the data into a higher dimensional space where a simple linear separation is possible without actually having to compute the coordinates in that huge space. It's computationally efficient magic.
Wow, okay. That is clever. So we've talked about individual models like linear regression and SVMs, but what if one model just isn't cutting it for a really complex problem? Can you team them up?
Absolutely. That's the whole idea behind ensemble learning. Why rely on one expert when you can consult a committee?
Makes sense. Strength in numbers.
Pretty much. There are a few main ways to do it. First is bagging, which stands for bootstrap aggregating.
Bagging. Okay.
Think of random forest. You train many decision trees, but each tree only sees a random subset of the data rows and a random subset of the features. They train independently.
So they each get a slightly different perspective.
Exactly. Then you combine their predictions, average them for regression, or take a majority vote for classification. This averaging smooths things out, reduces variance, makes the model more robust to noise.
Okay, so bagging is about averaging independent models. What else?
Then you have boosting. This is different. Models are trained sequentially. Each new model pays special attention to the mistakes the previous models made.
So it learns from errors.
Right. It focuses on the hard-to-classify data points. The final prediction is a weighted combination of all the models. Boosting is really good at reducing bias and often leads to very high accuracy.
Any famous boosting algorithms?
Oh yeah, AdaBoost was an early one. Then came gradient boosting machines, GBM, which use gradient descent to minimize errors. And then the real rock star, XGBoost.
The XGBoost, I hear that one a lot. Extreme gradient boosting.
Exactly. It's basically a highly optimized, supercharged version of GBM. It's known for its speed, efficiency, and often state-of-the-art performance. The extreme part comes from all the built-in tricks it uses to prevent overfitting, handle missing values smartly, and run really fast, even on large data sets. Think regularization, tree pruning, parallel processing.
So it's like GBM, but with all the bells and whistles for performance and stability.
That's a good summary. And then there's another important one, especially if your data has lots of categories, CatBoost.
CatBoost for categorical data.
You got it. Its superpower is handling categorical features like city, brand, department automatically and effectively, without needing you to manually pre-process them using things like one-hot encoding first.
Oh, that sounds incredibly useful. Pre-processing categories can be a pain.
It really can. CatBoost has clever ways to encode them internally during training. It also has good ways to handle missing values and prevent overfitting. Often, if you have a data set with many non-numeric features, CatBoost is definitely worth trying, alongside XGBoost.
Interesting. So different boosting flavors optimized for different things.
Exactly. And there's also stacking, where you train several different types of models, like an SVM, a random forest, maybe a simple logistic regression, and then train a final meta model that learns how to best combine their predictions.
Wow, okay. So ensembles are really about combining strengths.
Precisely.
We've touched on some powerful algorithms, but the field keeps evolving, right?
Yeah.
Deep learning is everywhere now, often linked to images or text. What's the core idea there? Is it just bigger models?
It's a bit more than just bigger. Deep learning typically involves neural networks with many layers, hence the deep. These networks are loosely inspired by the structure of the human brain.
Neurons and connections.
Kind of. You have an input layer, one or more hidden layers where the complex computations happen, and an output layer. Data flows through, and the network learns by adjusting the strengths or weights of the connections between these artificial neurons, usually through a process called backpropagation.
Learning by adjusting connections.
Right. They're incredibly powerful, especially for unstructured data like images, audio, and text, and when you have massive data sets. But they can be very computationally expensive to train, sometimes need huge amounts of labeled data, and can act as black boxes.
Meaning it's hard to tell why they made a certain prediction.
Exactly. Interpretability can be a challenge. For image recognition specifically, a type called Convolutional Neural Networks, CNNs, dominates. They have special layers, convolutional layers, that are designed to automatically detect spatial hierarchies of features. Think edges, corners, textures, then parts of objects, then whole objects. They're incredibly effective for visual tasks.
So they see patterns like our visual cortex might?
That's the inspiration, yeah. And then there's this whole other cutting-edge area, generative AI.
Creating things, not just predicting.
Exactly. Generative AI models don't just classify or predict. They create new content, text, images, music, code, you name it. One of the foundational models here are generative adversarial networks, or GANs.
GANs. Adversarial. Sounds dramatic.
It kind of is. A GAN actually consists of two neural networks competing against each other. You have a generator, which tries to create realistic fake data, say images of faces, from random noise.
Okay, the artist.
And then you have a discriminator, which acts like an art critic. Its job is to look at both real images and the generator's fake images and decide which is which, real or fake.
So they battle it out.
They do. The generator gets better at fooling the discriminator, and the discriminator gets better at spotting fakes. This adversarial game forces both networks to improve, leading to incredibly realistic generated content.
That's wild. So GANs can create fake faces, fake scenes.
Fake anything, potentially. Image synthesis, translating photos from day to night, creating art, enhancing low-resolution images, even generating synthetic data to train other models when real data is scarce. But they can be tricky to train and, of course, raise ethical concerns like deepfakes.
Right, the potential for misuse. Okay, with all these powerful models, from simple linear regression to complex GANs, how do we actually know if they're any good? How do we measure success?
Excellent question. Making predictions isn't enough. We need model evaluation. And for classification tasks, the cornerstone is the confusion matrix.
Confusion matrix. Sounds confusing.
Huh. It's actually designed to reduce confusion. It's just a simple table that compares the model's predictions against the actual true labels. It breaks down the results into 4 key categories.
Okay, what are they?
First, true positive, TP. The model correctly predicted positive. It said dog, and it was a dog. Good job.
Got it. TP, correct positive.
Then, true negative, TN. The model correctly predicted negative. It said not dog, and it wasn't a dog. Also good.
TM, correct negative. Okay.
Now the errors. False positive, FP. This is a type-I error. The model incorrectly predicted positives. It said dog, but oops, it was actually a cat.
FP, incorrect positive, like a false alarm.
Exactly. Think spam detection predicting something is spam when it isn't. You don't want too many of those.
Right. And the last one?
False negative F. This is a type 2 error. The model incorrectly predicted negative. It said not dog, but oops, it was a dog.
FN, incorrect negative, like missing something important.
Precisely. Think medical diagnosis failing to detect the disease that's actually present, often very high cost.
Okay, TP, TN, FP, FN. So how do these help measure performance?
They're the building blocks for all the main classification metrics. The most basic is accuracy, what percentage of predictions were correct overall, so TP plus TN, divided by the total number of predictions.
Seems straightforward.
It is, but it can be really misleading if your classes are imbalanced. Remember the 99% not spam example? A model predicting not spam always gets 99% accuracy, but is useless.
Right, accuracy isn't everything.
Definitely not. So we look at precision. Out of all the times the model predicted positive, TP plus FP, how many were actually positive? TP, it's TP plus FP. High precision means fewer false positives.
Quality of positive predictions. Okay.
Then there's recall, also called sensitivity. Out of all the actual positive cases, TP plus FN, how many did the model successfully find? PP. It's TP plus FN. High recall means fewer false negatives.
Ability to find all the positives. Got it.
Often, there's a trade-off between precision and recall. So we use the F1 score. It's the harmonic mean of precision, and recall gives you a single number that balances both. Really useful, especially for those imbalanced data sets.
F1 score. Balances the trade-off. Makes sense. And for regression, briefly.
For regression, we look at how far off the numeric predictions are. Metrics like mean squared error, MSE, mean absolute error, MAE, or R squared measure the average error or how much variance the model explains. Different ways to quantify prediction error.
Okay, great. So we've covered a huge amount today. From prepping data with EDA, understanding missing values, choosing algorithms like linear regression, SVMs, XGBoost, CatBoost, even touching on deep learning with CNNs and JANs, and finally evaluating performance with the confusion matrix and key metrics. It really is a journey.
It definitely is.
Yeah.
And it shows how interconnected everything is. Your EDA informs feature engineering, which affects algorithm choice, which impacts evaluation.
Absolutely. So as we wrap up, any final thought for our listeners as they continue exploring this field?
Yeah, maybe this. As you learn about different algorithms, try to think beyond just which one gets the best score on some metric. Ask why it performs well for a particular problem. What are its underlying assumptions? What are its inherent trade-offs, like interpretability versus raw accuracy? And how do those trade-offs align with the actual real-world goals of your project? Sometimes, a slightly less accurate model that people can understand and trust is actually more valuable.
That's a fantastic point. It's not just about the numbers, but the context and the why.
Exactly. Thinking about those deeper mechanisms can really empower you to design more innovative, more responsible, and ultimately more effective solutions.
Great advice. Keep digging, keep asking questions, and embrace that ongoing journey of discovery in machine learning. We certainly hope this deep dive has been illuminating for you. Thanks for joining us.